Now let's talk about some basic geographical concepts. So we won't be able to deal with GIS without talking about mapping, which is the process of building a map of something geographical. So maps basically are a world representation with, of course, some errors, because you cannot put as many details as the real world onto an image. Some basic properties of the maps are the scale, so how much reduced your map is compared to the real geographical element. So it can be in centimeters per kilometer and so on, so it's a definition. There is the orientation of the map, so is the north upwards and the south downwards, or is it something different, and so on. And there is the coordinate system, which we'll describe a bit more detailed later. And in the map, you usually have the geospatial data as a two-dimension picture, because you usually look at maps on something planar, such as a sheet of paper or your computer screen. So first, let's talk about the Earth shape. There are three basic Earth shapes that we can describe, and we'll see which one we can use for real mapping in a computer. So first, there is the geoid. It is this shape, so it seems like a potato. So it's roughly an ellipsoid, because your base shape of the Earth is an ellipsoid, but you have lots of peaks and holes here, because you have seas, which are holes below the sea level, and peaks, which are the mountains, for instance. And this kind of shape is very hard to model mathematically, because you have to keep all of the points and their altitude. If you want to model it, there is no simple model with an equation. So usually we don't use that as the base shape for the Earth. Then we have the sphere. We could tell that it's basically the shape of the Earth, but it's not exactly that. You know, the Earth is not exactly spheric, so we won't retain this kind of shape as the basic Earth shape. So last, we have the ellipsoid, which is the best overall Earth description. So this is this one. So it's close to the geoid, without all the weird feature of the real Earth, but there exists a mathematical model to describe an ellipsoid, so that's what we want, and it's accurate enough to be able to project from the ellipsoid coordinates onto something in 2D. So then let's talk about coordinate systems, which are used to represent a point on our ellipsoid in a mathematical way. So coordinates are defined by an origin and coordinates components, which makes it possible to describe a coordinate with its x, y, z, or such kind of coordinate component. So there are several types of coordinate systems. first you have the geographical coordinate systems, which are defined by latitude, longitude, and optionally altitude. So here is a model of geographical coordinate system. So we have Earth, it's this ellipsoid, with its center C, and on the surface of Earth you have a point P, whose coordinates in geographical coordinate system are defined by longitude, which is the angle between this meridian, which is the zero coordinate for longitude, and the angle here, so from C to 0 to C and the projection of P on the equator, and the latitude, which is the vertical angle between the equator here and the projection of P on this 0 longitude axis. And the size from C to P will be the distance between the center and the envelope of the ellipsoid where P is located. So then we have geocentered coordinate systems, which will be defined by Cartesian XYZ coordinates that we'll now take a look at it. So these are geocentered coordinates. So we have the center of Earth. We choose 3 axes, so Z will be through the pole, Y to the 0 geographical coordinate system, and X will be orthogonal to both. And when you have your point P here on the surface of the Earth, you project on Z, Y, and X, and you get XP, YP, ZP, P coordinates. Last, we have planar coordinate systems, which those are based on a 2-dimension projection. So here are, for instance, 2-dimension coordinates. We'll look at projections a bit later. So we have a grid with the coordinates. So here is our point, here is our 0, so we have X, Y, and we simply have to project orthogonally P on the Y-axis and X-axis to get its XY coordinates on the 2D planar coordinate system. So each type of coordinate will require a reference system with various information, such as its boundaries and so on. So here are some examples of coordinate systems. In geographical coordinate systems, the most known is WGS 84, which stands for World Geodetic System, such as returned by the GPS and other GNSS systems. So it gives you your coordinates as longitude, latitude coordinates. In geocentered coordinate system, you have ECEF, the Earth-centered, Earth-fixed coordinate system, which is used by the GPS satellites to track their own coordinates, and then by the GPS chip to compute your location before converting it to WGS 84. And in planar coordinate systems, you have Mercator, Lambert 93, all of the NAD North American datums, local coordinate system, and so on. So projections are maps that are displayed on 2-dimension physical supports, so paper, computer screen, and so on. and they require to convert a 3-dimension realistic coordinate to a 2-dimension representation at the cost of a loss in 1 dimension and some precision. So this is what we call the projection, which must project on some kind of surface, among whose conic projections, cylindric projections, and so on. So here is a cylindric projection. So you have your Earth geoid, ellipsoid here, its center, one point on the surface of the ellipsoid we want to project, and here the cylinder on which we'll project the coordinates. So you go from C to the point, then you have some mathematical expression to project on the cylinder. So here I prolonged the segment from C to P to the projected P. It's not that simple, it's a bit more complicated. Because your main problem, so here you see that P would be on this this part of the Earth, with a length of the whole. Here the perimeter here is less than the one of the equator, while for the cylinder each coordinate will be on a perimeter which is equal to the equator. So to avoid distorting the shapes of the shapes of the real geographical shapes, you have to scale your vertical coordinate to match the distortion between this perimeter and the new perimeter on the cylinder. That's why Mercator, which is a cylindrical projection, while keeping the angles correct, so the look of the shape is correct, it changes the surfaces values of the shapes. So that's why in Mercator projections Greenland and Russia seem so huge, because they are scaled up by the projection. Here is another kind of projection, which is the conic projection. So you have your cone, which with in relationship with the ellipsoid of the planet, is tangent somewhere. So usually you try to be tangent to close to the boundaries of your projection, which is quite small. So then you project on the cone from the planet, and the farther away from the tangent point you go, the more increased the distortion is. So those kind of projections are only for quite local projections. So for instance, the Lambert 93 projection is only for metropolitan France. So it's something like a bit more than 1,000 kilometers wide and high, to enclose all of metropolitan France territory, but it's not possible to use it in other remote locations such as New York or Shanghai. And that's why those projections are more accurate for their boundaries and not usable for other locations, and that's why there are a lot of conic projections for your each part of the world, and that's why America and China, for instance, they have several local conic projection, because only one conic projection cannot be precise enough to cover all of China or all of the United States of America, for instance. So let's talk about those projections properties. So there are two main properties to keep in mind. The equivalent property, which keeps the areas, which does not distort the apparent size of a given shape, and the conform projections, which can keep the angles. So they keep the global look of the shape, but it might be scaled up or down. So for instance, the Mercator projection is conform, so it keeps the angles, and it's cylindrical, but it's not equivalent, because it scales the areas up the further you go away from the equator. The Peters projection itself, it's cylindrical too, but it's equivalent and not conform. So it keeps the areas but not the angles. For instance, another projection is the Lambert 93, which is conform, it keeps the angles, and it's conic, but it's not equivalent. But if you remain in metropolitan France, it will seem equivalent because the errors are not big. So since there are a lot of coordinate systems and projections, one way to identify them and call these projections and coordinate systems easily is to use the EPSG, European Petroleum Survey Group, which defined some codes for each of the coordinate systems and projections. So, for instance, the EPSG 6171 on 4965 and 4171 define the RGF 93, which is Réseau Géodésique Français. The EPSG 4979 and 4326 define the WGS 84. EPSG 2154 is the Lambert 93 projection, which is bound to the RGF 93. EPSG 3395 is Mercator projection, and so there are literally hundreds of EPSG references and their coordinate systems and projections, which are linked to the EPSG code. So now, how do you convert WSG 84 to Mercator coordinates? So let phi be the latitude and lambda the longitude of your point to be converted, and lambda 0 be the map center in the longitude coordinate. So to compute x and y as 2D planar coordinates following Mercator, then we simply do for x lambda minus lambda 0. So for basically it consists in adding 180 degree to your longitude. And here for the y, so the latitude value, the vertical coordinate, you have to use phi as a radian value, so it's logarithm of tangent phi plus 1 on cosinus phi, and you get your y coordinate in the Mercator system.